As you may have heard, the FBI, in collaboration with various international agencies, disrupted the Qakbot botnet by directing infected machines to uninstall the malware. And if you're interested in malware analysis, which is probably why you're here, you might be wondering, how did the FBI do it? Well, join me as we use malware analysis tools and techniques to explore the code used by the FBI to dismantle the Qakbot botnet. Welcome back to the channel. My name is Anuj Soni, and today we are going to take a look at the FBI code used to uninstall Qakbot from hundreds of thousands of machines. Now, thankfully, as part of the Justice Department's announcement of the operation, they provided the hash, and I was able to use that hash to find the corresponding file on VirusTotal and download it for analysis. To save you a few clicks, check out the link in the description if you want to go ahead and download that file now to follow along. I've gone ahead and hopped into my Windows 10 malware analysis VM, and I have the content that the FBI delivered to infected machines right here on my desktop within this file named 7cde.bin. Now, to get started, I usually toss a sample into a hex editor like HXD in order to get a feel for the file format that I am dealing with. However, I've recently been experimenting with a tool called Malcat, so I'm actually going to use that for my hex editor here today. So I'm going to drag and drop this file into Malcat, which I have a shortcut for on my desktop. Now, this is the original layout that it shows you when you first load a file into Malcat, but for now, I just want to take a look at the hex output for this file. So I'll go to the top right here and click on this button. This is the icon that is a second from the left here on the top right. Now, before I go any further, I do want to warn you that I have a total of about 1 hour of experience actually using Malcat, so I am still very much learning about its capabilities. Perhaps in the future, I'll do a deeper dive into this tool. If that's something that interests you, let me know in the comments. Anyway, as we look at some of the bytes that make up this file, unfortunately, we do not see a 45A or MZ at the beginning, which would have indicated that this is a Windows executable. That would have been too easy. But taking a look at this content, perhaps it is shellcode. Now, if you're not already familiar with some of the opcodes associated with shellcode, don't worry about it. Let me show you how to quickly disassemble this content in order to explore the possibility that this is in fact shellcode. What you can do here is right-click on this first opcode and then choose Disassemble at offset 0. And you'll see now that it's translated each of those byte values into actual instructions. So seems like I begin with a call instruction here, which is actually represented by the opcode E8. And underneath it, I see a variety of other instructions that actually look kind of like code, right? If you were to disassemble something that is not intended to be code, it would look very, very different from this. Now, an E8 is a call to a relative offset. In this case, the relative offset is 0. So it would basically execute this next instruction, which is a pop. Now, one thing you'll notice is as I click on individual instructions here, on the bottom left, it's actually populating this pane here with information about the instructions. You'll see it's breaking it down, in this case, into the opcode and target. Now, of course, there's only really 2 components of this first instruction, so pretty easy to understand, but I really like this feature so far. And in the case that I'm encountering a more complex instruction, I could see this being very useful. You'll notice that a lot of the text is kind of this light gray color, a little bit hard to read. Well, part of that is because Malcat could use a little bit of guidance around the flow of execution here. As I just mentioned, this is a call instruction, and it's going to essentially jump to the very next instruction. In order to force Malcat to kind of reprocess this information, giving that flow of execution, one thing I can do is right-click on this operand here, and choose force function start. In other words, whatever operand is being called, right, the address, which is going to be the next instruction, interpret that as the beginning of a function. So if I go ahead and choose force function start, you'll see that some of the syntax is now highlighted, and it's a little bit easier to read. And that is, again, in part because I just forced the start of a function beginning at this pop instruction, which based on my interpretation of the call instruction is the beginning of a function. Now, as I scroll down just to get a feel for what other instructions reside here, you might notice that we see references to some individual characters here, KERNL32. So it appears to be at least some of the characters associated with kernel 32. I see a .d here, so good chance that it is dynamically building perhaps the string kernel32.dll. And as I scroll down further, see references to lots of hexadecimal values. One neat feature of Malcat is that in the case that stack strings are being used, or it's dynamically building essentially strings during execution, it can interpret some of that information. But again, it needs a little bit of guidance, in this case, in terms of the actual architecture that it is looking at. Well, if I scroll up here to the top, to this pop instruction followed by the push and move, I see what appears to be the makings of a prolog. Right? I have a push EBP followed by a move EBP ESP. This is typically what a function prolog looks like in x86. And so I can help Malcat further interpret this content here, this code, by telling it that these are x86 instructions. The way to do that here is if I go to the bottom right, you'll see there's a pull down that says no CPU. If I click on that and then explicitly choose x86, you'll see that it starts doing a little bit of work, and it's now able to actually tell me, hey, this is the beginning of the string kernel32.dll. And in fact, if I keep scrolling down, I start to see many other interesting references to strings, like virtual alloc, virtual free. We got virtual protect here. Many of these virtual APIs are ones that malware analysts typically focus on when debugging code, for example, because malware will often allocate regions in memory during execution and update permissions of regions in memory that are going to be executable. So this is certainly some interesting content, and Malcat has made it quite clear to me that these strings are actually being referenced by this shellcode. As I continue scrolling down to understand what content is referred to here, there's one other neat feature of Malcat that I want to call out, and that is these references to hash. You'll see one here as well as here. What this is basically telling you is that the hexadecimal value on the left-hand side matches a known API hash for loader load DLL. This is a native API. It's very similar to using the API load library, but this API is exported from ntdll.dll. Malware sometimes uses these native APIs in order to circumvent certain security monitoring and detection tools. And so Malcat is able to tell me that, hey, this is evidence of API hashing, again, a common obfuscation approach to obfuscate APIs that are used by shellcode. And specifically, it's able to tell me the actual API. Pretty cool, Malcat. Now, I could continue analyzing the shellcode by manually scrolling through and taking a look at individual instructions, but that can get pretty time-consuming and tedious. So in order to explore any functionality that might be embedded here, I'm going to turn to Mandiant's capa command line tool. As described on GitHub, I downloaded the standalone capa binary by clicking on this link, scrolling below to get to the assets, and then I downloaded the Windows zip file and unzipped it into my VM. I've placed the capa executable in my path, and so to take a look at its help output, I'll type capa-h, and there's a couple command line options that I want to highlight here. First, notice it's got this example of using capa to analyze shellcode, and it says that you have to use the -f option and specify the type of file format being analyzed. In this case, we are looking at 32-bit shellcode, so SC32 is the way to go. Now, you could run capa as is, and it will basically use its built-in rule set in order to identify any interesting capabilities. My preference, however, is to use the -r command line option, which allows you to specify a directory of rules. This allows me to add my own rules, but in addition, I can browse to Mandiant's GitHub repo for capa rules and download the most up-to-date set of rules that are available. The rules available on GitHub are generally more up-to-date than the versions that are built into the binaries. I'll also take advantage of the -v option in order to not only get details about which capability capa identified in a binary, but also the virtual offset of the code associated with that capability. I can then use that virtual address to pivot into the code using a disassembler like Ghidra. Now, you can also use a -vv option, which will provide even more context about the code as well as the rule, but I do find that output a little bit more overwhelming, and usually I just stick with the single -v option. So if I clear the screen here, in order to type our command, I'll type capa, followed by -f for format, specify 32-bit shellcode. I'm then going to include the reference to the actual file, followed by a -v to get output associated with the virtual offsets of any capabilities identified. Now you'll see there are three capabilities identified. First is that this code might contain obfuscated stack strings. We kind of already suspect that based on the Malcat output. The third capability identified here is that the code accesses the PEB, or the process environment block. That's actually not a big surprise because we already suspect, based on what Malcat was able to show us, that API hashing is being used, and API hashing usually involves probing the PEB for pointers to things like the DLL name and the name of an API in order to actually calculate the API hash. The third capability here specifies that the XOR operation may be used to encode or decode content. So let's take a closer look into this identified capability. Now, for more information on stack strings, you could, by the way, consider using a tool like Floss, but Malcat already provided us that information, so I'll leave that to you to further explore. Now, while I enjoyed using Malcat to initially view the code, I'm now going to turn to my primary disassembler, which is Ghidra. Now, unfortunately, the rest of the audio in my original recording did not get captured for some reason. So here I am the next day, ready to continue where we left off, and luckily, I'm wearing the same clothes. So let's go ahead and launch Ghidra. I'm going to double click it from my desktop. And by the way, while Ghidra is loading up here, I should mention that creating these videos clearly does take some time and effort. So if you're enjoying it so far, please do hit that like button. All right, so let me go ahead and create a quick new project here. And I will call this FBI Qakbot. And then I'll go ahead and drag and drop my shellcode file into that new project. And you'll notice I was about to press the OK button, but it is grayed out. That is because we are dealing with shellcode here. And so Ghidra isn't quite sure how to process this file, so I need to provide it with a little bit of guidance. In order to do so, I'm going to click on this button on the right-hand side of the language field. And since we're dealing with 32-bit shellcode here, I'm going to go ahead and search for x86. That gives me a smaller list of options to choose from. And I'll look at this size column, find the one that says 32, and also choose the row that has a compiler Visual Studio. And this usually gets me what I need in terms of Ghidra's processing. So I'll go ahead and press OK now, then press OK one more time. Allow Ghidra to load the file, press OK through the import results summary, and then double click on the bin file. Now, when Ghidra typically pops up this message asking if I want it to perform its auto-analysis, normally I click on yes. In the case of shellcode, however, I will usually click no here because I want to go ahead and manually disassemble the code. If I were to have clicked yes, Ghidra would not have processed this code and it would essentially look as it does right here. But I'm going to go ahead and press D on my keyboard in order to manually disassemble this content. It now looks closer to what I saw in the Malcat output. I'm also going to go ahead and close the scripting window at the bottom. Don't need that for now. At this point, once I manually disassemble the code, I will perform the auto-analysis in case it adds some value. Occasionally, it will change a few things, but sometimes you won't get a whole lot of added comments or context. But I'll typically do this by default, just in case Ghidra is able to help. So I'll press Analyze here, and since it is shellcode, which is generally much smaller than an entire Windows executable, it will perform its auto-analysis pretty quickly. Now, the reason I loaded the shellcode into Ghidra is to find and take a closer look at the code that performs XOR operations, which might be associated with some sort of encoding or decoding. At least that's what capa seems to be telling me. In order to get the address at which that code is actually located, I'm going to go back to my command prompt, and I see that it is the XOR operation occurs in the basic block located at this address. Now, one other point I need to make here. You need to pay attention up top to the base address specified by capa. This is the address in memory where the shellcode is located when capa analyzed it. And so all of the addresses referenced in this matches field are relative to this base address. Right now, the base address for my shellcode, you can see in the background there, is 0. And so in order to make sure that the addresses in the capa output match up with what I'm looking at in Ghidra, I'm going to rebase the shellcode in Ghidra. In order to do that, I'm just going to copy this address right here. And to rebase this shellcode in Ghidra, I'm first going to go to the top and click on this button where when I mouse over it says Display Memory Map. Once I have this memory map window, I'm then going to click on this house button. I'm not sure why it's a house. But if I click on the house button, it gives me an input field where I can actually insert a new address. I'll go ahead and paste that address that I previously copied from the capa output and press OK, and then close this window. And now we can see that the base address for my shellcode matches the base address that capa was referring to. One other point I'll make here, you'll see that as I click around on the right-hand side in the decompiler output, it looks gray and it says undefined function. This is an indication that Ghidra needs a little bit of help, just like Malcat did, in order to understand the flow of execution and to understand the structure of this code. Now, since I know that the first instruction is a call to essentially the instruction right here, and this is therefore the beginning of a function, what I'm going to do is right-click on this instruction, and choose in the context menu, create function. I could have also hit F on my keyboard, and this will tell Ghidra that this is the beginning of a function. Once I do that, Ghidra inserts its typical banner comment here, indicating this is the start of a function. And on the right-hand side, you'll see the gray background has disappeared, indicating that Ghidra is just a little bit happier. So now I'll hop back over to capa and grab the address in the matches field where it identified the XOR operation taking place. So I'll copy that address right there, hit G on the keyboard in Ghidra, and jump over to that location. Here it looks like we have a loop that is in fact performing the XOR operation. When I take a closer look at the operands, I see that it is XORing the lower 8 bits of EAX with 1 byte located at, well, whatever that points to. It's then performing a subtract operation right here, and then it moves the XORed byte located in the lower 8 bits of EAX to the address specified by ECX. So this begs the question, what sort of content is being moved into the address specified by ECX? The quickest way to answer that question is going to be to debug this shellcode. And in order to debug the shellcode, we're going to take advantage of a tool called runsc, which is maintained by a fellow SANS instructor named Evan Dygert. Runsc is going to help us accomplish 2 main objectives. 1, it's going to allow us to actually run the shellcode, and 2, it will allow us to attach to that running shellcode with a debugger. Let me go ahead and demo how to actually use runsc. I've already downloaded runsc from the GitHub repo and placed it in my path. So I'll open up a new tab here in my command prompt, and in order to use runsc, we're going to type in runsc32 followed by a -f, and then specify the actual file that contains the shellcode, in this case 7de.bin. I'll then go ahead and hit enter, and it now provides me with instructions that I need to follow in order to successfully attach to that process with a debugger. The first thing I'm going to do is to copy this address right here, which is the location in memory where the shellcode resides. So I'll copy that address. I'm now going to launch X32Debug. Once I launch X32Debug, I will attach to it by going to File, Attach, and then I will choose the runsc32 process by double-clicking on it. Next, what I'll do is set a breakpoint on the address that was in the runsc output. So I'll go down here to the command field, type BP, and then paste that address that I captured from the command line output, hit enter, and next you have to go back to the command prompt and hit enter. And this will basically cause the program to continue running, which should allow me to pause at the shellcode. So I'll hit enter here. And in the background on the bottom left, you'll see that I am now paused. And if I take a look at the specific instructions, this does appear to be the beginning of the shellcode. To actually find the loop where the XOR operation was called, let's go back to the code browser and remind ourselves that this loop began at the 44D offset from the beginning of the shellcode. So if I go back to runsc32 here and just scroll down until I get to 44D, this should be the beginning of that loop that we've been taking a closer look at, and I do in fact see the XOR operation right here. Now my objective with debugging this code was to identify what sort of content is being placed at the address specified by ECX. So what I'm going to do in this case is actually set a breakpoint by hitting F2 on the keyboard on the instruction after that move operation. Once I arrive here, I can inspect what is located at the address specified by ECX. So I'll go ahead now and hit this button to continue running the program. I've now arrived at that compare instruction, giving me an opportunity to, on the top right, inspect ECX and dump whatever's located at that address down to my dump window. And looking down on the bottom left, we see a 4D, which means we might be getting excited a little bit. But let's see what happens if I continue running the program. After all, we are in a loop, and if we arrive at this address again, perhaps we'll see what that next byte is that is placed at this location in memory. So I'll continue running the code by pressing this button. Looks like we do in fact have a 4D5A, which gives us some greater confidence that we might be looking at a Windows executable decoded in memory. But in order to confirm this theory, let's go ahead and remove this original breakpoint and set one after the loop continues all iterations. And then we can inspect the bottom left to see additional content that might reside at this location in memory. So now I'll continue running the program. And it does appear to be the beginnings of a Windows executable. We see the common string, this program cannot be run in DOS mode. And as I scroll down, I see what appears to be the beginning of the PE header. And as I continue scrolling, I see references to the various sections that typically comprise a Windows executable. And then the beginning of what looks like the first section here, which is likely the .text section containing executable content. So in order to take a closer look at this information, let me go ahead and just dump this down to disk. I'll right click and then go to follow in memory map. I'll right click again on the selected region in memory and then choose dump memory to file. I'll place this on the desktop and call it dumped.bin and hit save. Going to my desktop now, here I have dumped.bin. I'll go ahead and drag and drop it into PEStudio for some additional confirmation that this is in fact a Windows executable, and PEStudio does identify it as a 32-bit DLL, and we can also observe a compile time of August 16th, 2023, which is just a week or two before the FBI's operation took place. Now, of course, you could continue to take a look at PEStudio output, which would be a valuable next step, but we're going to skip ahead and try running capa against this dumped executable now. So I'll run a very similar command line to what I did before, and I'll type capa, followed by the dumped executable name, followed by -r to specify my rule set that I've downloaded, and then a -v so I get information about virtual addresses of the various capabilities that capa identified. Now, there's obviously a lot to digest here, and we don't have time to explore it all, but I do want to call your attention to a select few of the capabilities, namely the first three identified, which have to do with the use of named pipes. We see a reference to connect pipe, read pipe, and write pipe. In all three of those cases, the address, the virtual address of the matches occur at the same address. So let's take a closer look at these identified capabilities. Now I've gone ahead and already loaded the dumped executable into Ghidra here. So I'll hop back over to the capa output, copy one of these pipe related addresses, go back to my code browser, hit G on my keyboard and paste that address. Once I arrive at this function, if I use the decompiler output to accelerate some of our analysis, I do see references to what looks like a named pipe, and I also see a reference to an API named call named pipe A. If you look up this API on Microsoft.com, you'll find that it can basically connect to a named pipe and then write to that named pipe as well as read from it. In this case, the named pipe is going to be referenced as the first argument, and the second argument is going to contain an address that points to data that is going to be written to the named pipe. If we want to get further insight into what that named pipe is and what data it is writing to it, we can further debug this process. So I'll go back to runsc32, hop over to my CPU window, and I'll set a breakpoint on that API we just identified. Call named pipe A. I will then proceed to continue running the program by hitting this arrow button. And now we've arrived at the call to call named pipe A. And just for clarity, understand that we are now in the decoded Windows executable in memory. That's what's being run right now. If I take a look at the first argument by dumping this value right here to my dump window, I'll see a reference to a named pipe on the bottom left. And if I want to take a look at what it is actually writing to that named pipe, I'll hop over to dump window number 2, choose this second argument, and then again, right click and go to follow in dump. And what we see here is that it is writing the value 4. Now, SecureWorks did a great write-up on what is happening here, which I encourage you to read, and I'll include a link in the description. But the basic idea is that Qakbot uses named pipes to communicate between processes on an infected machine, and the value of 4 essentially tells the malware to shut down. Nice. So there you have it. That is one approach to exploring the FBI's Qakbot Takedown code. If you enjoyed this video and want to see more like it, please do subscribe. And since you're here, you might want to check out some of the other videos I recently uploaded. I'll see you next time.